In this video, I'm going to talk about linear regression with one multi-categorical predictor, and I'm going to illustrate doing it in the R statistical computing environment. And we're working with the currently visible portion of the regression demos.r code file. So here we are back in R. And before we fit the model, let's think about our predictor. We're going to use color to predict price now. We just got through using material to predict price. Material was binary. Color has 4 categories: black, blue, green, and red. And here's the counts for the 4 categories in this sample. In order to understand how it's going to be used in the regression model, it's nice to look at the contrasts. So here, the set of contrasts is a little bit more complex than the example with material, but it still gives us information about what indicator variables we're going to need when we plug this factor into a regression model as a predictor. Blue is going to represent a column of zeros and ones, where all the blue robots are coded as 1 and everything else 0. Green is going to represent a column of zeros and ones, where all the green robots are coded as 1 and all the rest 0. And red is going to represent a column of zeros and ones, where all the red robots are coded as 1 and all the rest 0. And the black robots are those that are not coded as 1 for any of these 3 contrasts. So they represent the reference category here. I'm fitting the model the same way. Price is the response variable. Color is the predictor. Color is stored as a factor, so I can trust R to handle including these contrasts in the model instead of trying to use color as a single variable in some way. So here's the model summary. Now we get 3 slopes instead of just 1. Even though those 3 slopes together kind of represent 1 conceptual variable, they're, in a more literal sense, 3 variables. This one compares blue to the reference category of black, this one compares green to the reference category of black, and this one compares red to the reference category of black. And that means that the intercept is the mean for the reference category for the black robots. The black robots cost $104.86 on average. The blue robots were $2.64 more expensive than that. The green robots were $5.14 less expensive than those black robots. And the red robots were statistically significantly less expensive than the black robots. The blue and green robots did not differ significantly in price from the black robots. We can, of course, also call confint in order to get confidence intervals for this intercept in these 3 slopes. So this confidence interval from 100.97 to 108.75 represents a 95% confidence interval for the value of the mean price for the black robots. And each of these confidence intervals is estimating the discrepancy in price between the corresponding color of robot and that black robot reference point. And we can reassure ourselves that this worked properly by looking at the actual computed means for each color of robot. Again, I'm using tapply. Price, the first argument, is the numeric variable that I want to apply the mean function to. Color, the second argument, is the categorical variable that I want to use to group the prices before applying the mean function to each group. And mean is the function that I want to apply. So this is going to calculate the mean, removing missing values, of the price of the robots within each of the color categories separately and give me the result in a vector like this. The black robots were $104.86 on average, just like the intercept told us. The blue robots were $107.51, which is $2.64 higher than the mean for the black robots. The green robots were $99.72 on average, which is $5.14 less than the black robots. And the red robots were $97.25, which is $7.61 less than the value of the black robots. And the red robots were the farthest away from the black robots in price. And that might be a clue as to why the difference between the red robots and the black robots was statistically significant, whereas the other differences were not. Again, I want to really harp on the point that R is automatically converting the color factor to numeric dummy variables to include it in this regression model. So I'm going to manually make those numeric dummy variables to illustrate what's going on. Here, I'm creating a numeric version of the blue indicator variable by testing which colors are equal to blue, converting them to numeric, and storing the result in a new column of the data frame called blue, doing the same for green and red. And here is an illustration of the result. Here's the color column, the first 20 rows of the color column of the data frame robots, and the first 20 rows of our 3 new variables in that same data frame. And we can see that blue has a value of 1 for all the blue robots and 0s for the other colors of robots, and green and red correspondingly. Here's the original regression summary again that has the color factor as the predictor of price. And here is the result of calling LM on this formula, which has price as the response variable and 3 predictors. We have a main effect for blue, a main effect for green, and a main effect for red, separated by plus signs in this single regression model formula. And if I scroll up a little bit so you can see parts of each of these model summaries, I hope you can reassure yourself that they are precisely identical. When a 4.86 represents the mean for the black robots, these values represent the differences between the black robots and the other colors of robots, and all the numbers are exactly identical between these 2 ways of fitting this regression model because they are the same. These indicators, blue, green, and red, representing columns that have 0s for all of the other colors and 1s for the named color, are precisely the same contrasts that we saw that R was planning to use anyway when we plugged the color variable into the regression model. So far, with this standard model summary, we have comparisons between blue and black, green and black, and red and black robots. But we haven't yet had a chance to compare, for example, the blue robots to the green robots, or the blue robots to the red, or the green robots to the red robots. So what if we wanted to do that? The easiest way to do that most of the time, I think, is to re-level the color factor to alter the contrasts. This is a very handy function that takes a factor as its first argument, and in its most common use case, specifies a new reference category for that factor as its second argument. So we're going to take the color factor and redo the contrasts so that blue becomes the reference category. And we're going to assign the result to the same factor again. So this will change the factor to a copy of itself that has blue as the reference category instead of black. And let's just visualize what that did. Previously, we had contrasts called blue, green, and red, and now we have contrasts called black, green, and red, and the black contrast has 1 for the black robots and 0 for the other colors, and the blue robots are the ones that are 0 for all 3 contrasts, so they will be the new reference category. So when we run this model summary of price tilde color after changing color in this way, then we get a table where blue is the reference category. The blue robots cost $107.51 on average, and each of these slopes represents a comparison between another color and blue. And we already knew that the black robots were not significantly different from the blue robots. We got that comparison even when black robots were the reference category. But these 2 comparisons are new. The green robots are $7.78 less expensive than the blue robots. And we knew the discrepancy between them because we've already seen the means, but we did not have a formal hypothesis test of whether the green robots and the blue robots were statistically significantly different before, and they do seem to be. The red robots are also significantly cheaper than the blue robots. There's one comparison that's still missing, which is the comparison between green and red robots. We haven't seen that. So let's re-level the color factor again to make green the reference category. And we've already seen the green and blue comparison, and we've already seen the green and black comparison in the previous 2 models. But here we get the comparison between green robots and red robots. This is new, and so we have finished comparing each pair of colors of robots if we would like to do that. Let's do one more example with a multi-categorical predictor. And in this case, I would like to use the practicality rating instead of the price as the response. I want to see how color is associated with ratings of how practical the robot is. So here's the practicality rating. It appears to be nicely symmetric. There's nothing concerning about its distribution. And here are the mean practicality ratings for each color of robot. So it seems that participants thought the black robots were most practical and the red robots were least practical. And we would like statistical hypothesis tests of the differences between these four types of robots. So we're going to plug color in as a factor predicting practicality ratings in a regression model. And I'm going to relevel color ahead of time to make red the reference category, and we'll cycle through a few other reference categories. So here I've called the LM function with practical as the response variable and color as the predictor. Color is a factor, so it's going to get its contrasts are going to get included. We've just releveled it so red is the reference category, so those contrasts are going to be green, blue, and black, all compared to the red reference category. And I plugged it directly into the summary function because I don't need to store the result of this LM because I'm not going to use it for anything else other than this illustration right now. Hello, yes, I'm finishing this part of the recording on a different day. Anyway, now we have a summary table of a regression model where the practicality rating is the response variable and the three indicator variables representing color are the predictors, and the red color is the reference category because red is the color that's omitted from the three indicator variables shown here. And so the results indicate that the green robots were very slightly more practical than the red robots, and that difference was not statistically significant. The blue robots were perceived as almost a quarter of a scale point more practical than the red robots, and that discrepancy was just barely large enough to be statistically significant. And the black robots were perceived as 0.63 units more practical than the red robots, and that discrepancy was large enough to be statistically significant. All I'm going to do is change the reference category to green and show some additional comparisons. So we already knew that the red and green robots were not significantly different, but we have two additional comparisons here. The first one indicates that the blue robots were perceived as 0.15 units more practical than the green robots. That discrepancy was not large enough to be statistically significant. And then the black robots were perceived as more practical than the green robots, and that difference was large enough to be statistically significant. So if I show the means on the screen again, I can illustrate a key point about these results. The red robots were perceived as the least practical, and the green and blue robots were both perceived as slightly more practical than them. But the red robots were perceived as significantly less practical than the blue robots. The green robots did not significantly differ from the red or the blue robots. This kind of result sometimes throws students off, but there's nothing unusual or wrong about it. It's totally reasonable to make the point that the gap between the red and blue robots in our observed data was large enough that such a gap would be unlikely to arise very often due to chance in a world where red and blue are equivalent. But the green robots fell between the red and blue robots in our data, leading to inconclusive results about those green robots relative to the red and the blue. So the gap between the green and the red was not large enough that it would be unlikely to arise due to chance very often in a world where green and red are equivalent, but the gap between green and blue was also not large enough that it would be unlikely to arise due to chance in a world where green and blue are equivalent. And so although we have enough evidence that we might be tempted to argue that red and blue are not equivalent here, we are not sure whether green is similar to red or similar to blue. There's one comparison that's missing from the contrasts that we've seen so far, so I'll change the reference category to blue for completeness and show that the blue robots were perceived as significantly less practical than the black robots. That is, this slope is positive, indicating that black was more practical than blue, and that discrepancy is statistically significant. These other two comparisons we have already seen. So in a world where your results actually look like this, you might be tempted to argue that you have enough evidence to claim that red and blue are not equivalent when it comes to marketing the practicality of robots. But it is also important to keep in mind that this p-value is only just barely below 0.05, and it would arise due to chance around 1 in every 20 experiments if red and blue really were equivalent, and so you might want to temper your expectations about the discrepancy between red and blue until you've reinforced that result. The main point that I want to make here is that it is totally normal for a multi-categorical variable to produce results where some of the categories are statistically significantly different, and yet other categories fall between them and are not different from either of the more extreme values.